All right, guys, so this is going to be the notes over wave types and parts. I'm going to go through the notes, and then below there will be some resources in case you want clarification on certain things. There's a couple of things I'm going to have to ask you to get clarification on just because I can't, in the current circumstances, demonstrate them, and so it might be easier for you to visualize what's happening by looking at those resources. All right, so with that said, let's get started. First of all, a wave transfers energy without transferring matter. And so that's the key distinction between a wave and anything else. So for example, if I want to get the energy of a tennis ball from one point to another, I have to physically move the tennis ball from point A to point B. But if I want to get the energy in a wave from one point to another, I just have to create the wave. The thing I'm making the wave in stays relatively in place, but the energy moves through the wave. Okay? So the first type of wave is a transverse wave. So transverse waves tend to move in your stereotypical wave motion manner, where you've got these series of ups and downs, ups and downs, ups and downs. And the important thing is the motion of the wave is going to be up and down. It doesn't have to be up and down. It could be side to side, but the motion of the wave is moving in some manner with the medium that it's moving through. It could be up and down. It could be side to side. But the important thing there is that the motion is up and down or side to side, and the energy is going to be transferred along a path of the medium. So it's going to be like if this is point A and this is point B, the energy is being transferred from point A to point B, but motion is going to be up and down. And so in a transverse wave, motion and energy are perpendicular to each other. Okay? Now, a longitudinal wave is a little bit different. A longitudinal wave, instead of relying on up and down motion, relies on side-to-side motion. And so in a longitudinal wave, and I'm going to try drawing this, and it's going to look terrible. You'll just have to bear with me. So I've got areas of what are called rarefaction, where the wave is spread out. So don't imagine these as, don't imagine what I'm drawing as like actual what's happening. Imagine these as like wave fronts. It's like imagine these as like if you're looking at the ocean, like wave fronts coming through. And in a longitudinal wave, you've got series of compressions and rarefactions. So these areas right here are known as compressions, and then these areas right here are known as rarefactions. And the important thing for this is that the motion is going to be back and forth, and the energy is going to be back and forth. And so in a longitudinal wave, the motion and energy are parallel to one another. Okay. Now, I'm going to try to draw what it looks like in sound. In sound, like just so you can imagine this, like you've got particles in air. So for sound, you've got these areas where the particles are going to be fairly spread out. And then you're going to have other areas where those particles are going to be more densely packed. And that is going to be the areas of compression and rarefaction. So if you're dealing with a sound wave, it looks a little bit more like this rather than like the front I had. But basically you get these areas where the particles are rarefacted and parts where the particles are compressed, and that's how sound moves through the air. So whenever someone talks to you, sound is actually being transmitted because your vocal cords are compressing compressing the air and then rarefacting the air, and that is sending a wave through the air. So that wave then travels through the air, enters and hits your eardrum. So particles from like my mouth when I'm talking to you do not go traveling through the air, hit your eardrum, and that's how you hear it. It's a wave front that moves through the air. Okay, so next up we got the parts of the wave. All right, this is something that is important to know. And so I'm going to draw the wave as we go. You'll have to forgive me. I hope you can, because I don't have a great way to draw this on here, and I am an awful drawer, but I hope you can forgive me. So first of all, the substance or material the wave travels through is known as the medium. So the medium is what the wave travels through. It is the in sound, it's air. So whenever you're talking, air is the medium. If you're at the ocean, the water is the medium. If you are making a wave on a string, the string is the medium. So the medium is just whatever the wave is traveling through. So the next thing before I start drawing is going to be the midline. The midline is the baseline of a wave when it's at rest. So this line right here, boom, 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 is going to represent our midline. And then for this example, whoops, I just butchered midline, didn't I? Okay, hang on. So for this example, what we're going to do is we are going to go ahead and draw, man, I am just terrible at spelling today. I am going to draw a transverse wave. Now, transverse waves are typically the way waves are represented, but that doesn't necessarily mean that the same things don't apply to longitudinal waves. It's just easier to visualize this with a transverse wave. So here's the transverse wave. All right, let me try doing that again. Try to make it a little more even. That was a little better. Again, apologize, I'm terrible at drawing. Okay, so the first little question here is at the top point of the transverse wave, this is known as the crest, and the bottom point is known as the trough. So the top part here, that's the crest. The bottom part here is the trough. Okay? How high the wave is from the midline to the top of the crest, that is known as the amplitude, and it can be measured, it's measured from the midline to the crest or the midline to the trough. Either way, it's known as the amplitude. The important thing is it's not the whole distance from the crest to the trough. It's the midline to the crest or the midline to the trough. Okay, now, let's see. All right, give me 1 second. Okay, so now we're going to keep going. I know that this is a lot of stuff, but it's not, it's just basically definitions. So we're going to keep carrying on here. So next up we've got the wavelength. Wavelength. So the wavelength, I'm going to change the size here. The wavelength is basically the distance between two consecutive points on a wave. Now, it can be any two consecutive points, but it's easier if you try to imagine the points as being, or it's easier to find it if you use one of the three methods that we're going to go over. Also, you should know the wavelength has a symbol. This is the symbol for the wavelength. It's known as a lambda. Sometimes you'll see it done as a script. It's a Greek letter. It's a Greek letter L. Sometimes you'll see it as a script, and sometimes you'll see it as less of a script and just more of a stick. Basically, it's an upside-down Y. But that is the wavelength. And you essentially can measure the wavelength in three different ways. You can go from crest to crest. You can go from trough to trough, or you can go through three nodes. All right, so we're going to talk more about nodes in a second, but the nodes are right here. So you can go through three nodes, 1, 2, 3 nodes. This is a wavelength. When you're counting nodes, you go 1, 2, 3. So 1, 2, 3, and then this one is your first one for the next wave. So the third node is the first node on the next wave. Okay, so that's wavelength. All right, next up, how many waves pass per second? This is known as the period. So the period of the wave. How many waves? Oh, I'm so sorry. How many waves per second? This is known as the frequency. The frequency is the number of waves that pass per second. So you can think of the formula here in two waves. You can do the number of waves over the number of seconds, or you might use the frequency is equal to 1 over the period. And so what is the period? The period is how many seconds it takes to make one wave. So the period is the number of seconds per waves, or period is equal to 1 over the frequency. So you should notice here that both of these are inversely related to one another. So you can just flip them if need be. The frequency and the period are indirectly related. If you raise one, you lower the other. And so that is that one. So next up we've got the velocity, which I know the definition is kind of stupid. The velocity is the speed of a wave. Velocity is equal to the frequency times wavelength. It's also dependent upon the medium. So keep this in mind. It's dependent upon the medium. All right, so whatever the medium is determines the speed of the wave. So air has a specific speed for sound. It's 340 meters per second. Water has a different speed for sound. Steel has a different speed for sound. The speed of a string is determined by how tight the string is. So the tighter the string, the different. Basically, if you tighten a string, it changes the medium and it changes the speed of the wave through it. The tighter the string, the faster the wave travels through it. The formula for the velocity is V is equal to lambda f. But you can also write it as V is equal to lambda divided by the period. So in a given medium, the velocity will stay constant. So in a given medium, V is going to be constant, which means that this relationship, if the wavelength goes up, the frequency has to go down, or if the frequency goes up, the wavelength has to go down. But notice the reverse is true for the period. If the wavelength goes up, the period also has to go up. All right? So the wavelength and period are directly related, wavelength and frequency indirectly related. So wavelength and frequency indirectly related, wavelength and period directly related. All right? A point where the wave crosses the midline. So a blank is a point where the wave crosses the midline. This is known as the node. So the node is the point where the wave crosses the midline. So here's the wave crossing the midline. That's the reason we called this a node earlier. And an antinode is a point at the top or the bottom of the trough. So at the top or bottom of a trough. So like an antinode would be here or here. So basically an antinode is the crest or the trough. It doesn't really matter which one. All right. The part of a longitudinal wave where the particles are compressed together, these are known as the areas of compression. We showed that earlier. The areas of compression were right here. And the part of the longitudinal wave where the particles are spaced apart is known as the areas of rarefaction. And again, you can find those areas over here. So compression right there, rarefaction right here. Okay? Last few things. The energy can be determined by either the amplitude or the frequency of the wave. So in a mechanical wave, in a wave that, in most waves, the waves that we'll be dealing with probably, the energy is related to the amplitude squared. Now I'm using that little symbol because this isn't the exact formula, this is just the relationship you need to know. But for light, energy is related to the frequency. So that's actually the formula for energy of a light wave. The higher the frequency, the more energy a light wave has. But for a mechanical wave, it's the amplitude that's important. And so if you just have to pick one thing to know, make sure you know this one, okay? So energy is related to the amplitude of a wave. Finally, we've got a pulse. A pulse is a single wave that moves through the medium. So imagine, if you will, that you're standing in one place holding a string. Maybe it's tied to a door, and you just raise your hand up and down one time, give it a little flick. What you would send through is a pulse wave. A periodic wave is a wave produced by a continually oscillating source. Oscillating just means to be moving, continually moving source with a constant frequency. So if you are, instead of just doing one little flick, if you just do the same flick motion over and over and over again, you're oscillating now, and you've created a periodic wave. So a periodic wave, again, is created by is a constant frequency. If you just open your mouth and create one sound like this, then you've created a periodic wave. By the way, that sounds way stupider in a room with no one in it than it does whenever I have a group of you in here. I think that gets us through the wave types and parts. I realize that you may or may not have got all that. If you didn't get all that, I'm sorry. I hope you can go watch it again. And if you need some clarification, some of these things, I mean, they just are what they are. So like wavelength, frequency, period, velocity, node, antinode, all this stuff, they're just the way the way they are, and you'll just have to practice on some of the problems we give you. For transverse and longitudinal waves, if you're having trouble understanding those, I will definitely put a link in to help you understand that at the bottom of the assignment. Okay? All right, well, I'm wishing you all the best of luck, and I'm going to make the second video now.